In section 4.3, we're going to take the seemingly unrelated sections of 4.1, which was about finding antiderivatives, and 4.2, which was about finding area under a curve, and tying those two concepts together. Okay, quick review about finding or approximating the area under a curve. So in this particular picture, I have 14 rectangles drawn. So if I wanted to approximate the area under this curve from A to B and above the x-axis, I would take those 14 areas and add them up. As we talked about in 4.2, that can get quite tedious to write out R1 plus R2 plus R3 and so on. So we resorted to using sigma notation or summation notation. This notation is telling us to sum up or to add all the areas of the rectangles, which is big R, from 1 to 14. And again, that'll get us an approximation for the area under the curve. The way we found the areas of these rectangles was just our good old formula of base times height, but we did a little bit of changing to that formula to kind of make it more useful in the xy plane. And the way we found the area of a rectangle in the xy plane is we found a y value, which was f of x, times a change of x, which is the base. So it's still base times height, but just written in a little bit different manner. One of the things we realized from 4.2 is that as we increase the number of rectangles, our approximation becomes more and more accurate. So let's go ahead and take a look at this picture and kind of recap that. So I have this one rectangle that's kind of highlighted here, and of course we're trying to determine the area of this yellow region here. So approximately the area is equal to the sum of the areas of the rectangles. Not perfectly, but it's an approximation. So the way we can write this is in this manner. We're going to still use summation notation, but now I don't know how many rectangles I'm using. So instead of having it go from 1 to 14 like you saw above, now it's going to go from 1 to n being any amount of rectangles we want to use. And of course we know the area of a rectangle is the base times the height. I'm going to just write it in a different order as height times base. The way we determined the height of these rectangles was an f of x. The base was a little change of x. So I'm going to go ahead and label that on my picture here. Our base of our rectangle is a little change of x. And that's going to happen at some x value that I'm going to call x sub I. To find the height at that x value, of course, that would just be f of x sub I. So the height of this rectangle would be f of x sub I, just like you see above. These two are the same. I'm just using that subscript of I to indicate any x value from A to B. And then of course we're going to multiply by the base, which is delta x. That thing is what we call a Riemann sum. If you recall from 4.2, I mentioned something about a Riemann sum, but now you know what the Riemann sum is. It's just another way of saying we're adding up the areas of a bunch of rectangles, and that n at the top of the sigma notation, if it's a 10, would just mean 10 rectangles, or if it's 1,000, it would just mean 1,000 rectangles. So that's kind of where we're at. I could have covered this in 4.2, but I wanted to wait till 4.3 to talk about this. But that's still an approximation. You'll notice I used the little squiggly equal sign for the approximation because it's not going to give us an exact value. If we want an exact value, it's possible to do that, but we have to squeeze in an infinite amount of rectangles. And as we do that, we're going to have to realize that the width of each rectangle is approaching 0. As we squeeze more and more rectangles in there, the base of those rectangles are going to get smaller and smaller and smaller, or in other words, they're going to approach 0. So now I'm going to kind of still use this sigma notation, but I'm going to kind of exaggerate it a bit. Instead of using that Greek symbol sigma, I'm just going to write a big S, and we're going to all agree that that big S, represents an infinite amount of rectangles that we're trying to add up. And of course, again, the area of a rectangle is just the height times the base. So that n that you see over here in this Riemann sum, which is the number of rectangles, we're letting that go to infinity. When we write this big, long, stretched out S, that's what I'm saying. We're just agreeing that that's my way, I guess, of saying that that's an infinite amount of rectangles. So again, we know the height of these rectangles is some f of x, and we know the base of these rectangles is a little change of x. If we rewrite that little delta x, which is a change of x, as a dx, which would still be kind of the same thing, we end up with this notation. And if we take it one step further and drop off that we get why that symbol for integration is used. When we use this symbol for integration, not only does it mean we're trying to find the antiderivative, but it also means we're trying to find the area under a curve with an infinite amount of rectangles. When we do that, we have to put this A and this B because that's indicating what we're finding the area from where to where. So it could be from 0 to 1, 10 to 20, whatever the case might be. So a function and the equation for the area between its graph and the x-axis are related by an antiderivative. Quite remarkable discovery that was made. Just by adding up an infinite amount of rectangles, that actually is related to finding an antiderivative. So anytime you see this thing called a definite integral, and really the only thing that's changed from 4.1 is now we have this a and this b, which makes it a definite integral, so it's defined from one value to another. That's telling you to find the exact area. That's the key here. It's an exact area under the curve f of x and above the x-axis from a to b. We call the a the lower bound wherever we're starting, and we call b the upper bound wherever we're ending. Okay, so now we have this Riemann sum and area under the curve and integral kind of all tied together. So now this is a very important kind of thing to kind of finalize and make sure the concept is solid. We know a definite integral is the limit of a Riemann sum. And think about how we discovered that from the last slide. We know that this part right here is a Riemann sum. And if we want that Riemann sum to give us the exact area under a curve, we need to let that number of rectangles go to infinity. This is just us squeezing in an infinite amount of rectangles under a curve. And we now know that taking an integral from one value to another value gives us an exact area under a curve, which we related to an antiderivative. So again, kind of two very seemingly unrelated topics, but they're tied together and they kind of mean the same thing, or one is dependent upon the other. So as that little delta x, which is the rectangle width, gets smaller and smaller and smaller, the number of rectangles approaches infinity and that area becomes exact. One thing that comes up when we're talking about our ability to find an area, and I think it hopefully is a little bit intuitive, is that if we have a continuous function, we know we can integrate it. Or in other words, what this theorem is saying is if a function is continuous from a to b, we know f is integrable from a to b. Or in other words, it just means we can find the antiderivative, or a value from a to b for the area. So just like when we study derivatives, we have to be really, really well versed in what we're thinking, seeing, or hearing whenever we see this definite integral. Anytime you see a definite integral, the very first thing you should be thinking about is that represents the area under a graph, but above the x-axis. The other thing it represents is an antiderivative. And again, those two things we thought weren't related from 4.1 and 4.2, but based on what we've been talking about this lesson, it turns out they actually are related to each other. The other thing it represents is, of course, a definite integral, and that definite integral, like we saw above, is just another way of saying we're taking the limit of a Riemann sum as n goes to infinity. Okay, now that we have the two concepts related to each other, an antiderivative being related to finding the area under a curve, now we can focus on the details that we need to deal with when finding areas under curves. So when we're finding the area under a curve from A to B, if we have area above the x-axis, we define that as positive area. If we have area below the x-axis, we define that as negative area. And of course, if we're trying to find the area from A to B, we would add the areas above the x-axis and subtract away the areas below the x-axis. That is what we call net area. So we're ready to kind of take a look at our first area example, or our first definite integral example. If I temporarily, I suppose, scribble these two bounds off, the lower and the upper bound, that would have been a problem like you saw back in 4.1, where we would have used the power over integration to find the antiderivative. But since we have bounds on this integral, and that makes it a definite integral, we really don't know how to solve that yet, or we haven't talked about how we'd even solve that when we have those numbers there. So the good news is we can actually graph this picture and answer this geometrically or visually. If you graph the function x minus 1 from 0 to 3, you just end up with two triangles. You'll end up with a triangle from 0 to 1 below the x-axis, and you'll end up with a triangle from 1 to 3 above the x-axis. So we actually don't even really need to know how to find antiderivatives and all that from 4.1. We just need the concept that we learned here, is that this definite integral represents the area from 0 to 3. And since we can find the area using just simple geometry, we can go ahead and proceed. We know to find the value of this definite integral, we'd have to take the area 1, which is positive, and subtract away the area 2. To find area 1, we'll just take the base times height, which is 2 times 2, and divide by or multiply by half. To find area 2, we'll take the base and the height, which are 1, and multiply by a half. When you do that math, it turns out nice and simple. That definite integral, or the area under the curve, is 1.5. There's some other properties we need to realize when we're dealing with definite integrals, and I think this one, after you think about it for a sec, makes perfect sense. Why is the integral from one value to that same value from a to a 0? Well, we know that this is a definite integral, and it represents area. If you integrate, or if you want to find the area from one point, and that next value is the same exact point, we've gone nowhere. We've defined no region. So of course, the area would be 0. So just as a quick example, it doesn't even matter what equation we have written here or what function we have written here. If your upper and lower bound are the same, your integral will always be equal to 0 because the area is equal to 0. From time to time, you're going to have to watch out for this. You'll notice that we call the a the lower bound, and we call the b the upper bound. In other words, a has to be smaller than the b. Every once in a while, you're going to run into a problem that switches that on you. And it turns out that's not a big deal. If you want to switch the bounds on your definite integral, it's totally legal. You just need to put a negative in front of that integral. So as an example, if you saw the integral from 3 to 0 of x dx, that doesn't quite look right because we want the 0 on the bottom and we want the 3 on the top to be written a little more properly. We can switch those. All we need to do is put a negative in front of that integral. One other property of integrals that you guys are going to need is the additive property of integrals. From time to time, you're going to get an area that gets split into two pieces. And because things are written in a way that kind of might confuse you if you're not quite sure of what is being given to you in a problem, you need to realize that if you have an integral from a to b, you can split that into two integrals. You can split that into the integral, in this case from a to c, and from c to b. And since we realized that this represents the area from a to b, we would just need to add those two areas together. Okay, let's practice evaluating some more definite integrals. Here we want to evaluate the definite integral from 2 to 4 of 1/2 x cubed minus 3x plus 2 dx. And then they give us a bunch of information at the bottom. Just to make sure we're all on the same page, if I were to scribble out this upper and lower bound of 2 and 4, that problem would be like a 4.1 problem, and we could apply the power rule to find the antiderivative. Unfortunately, it's got bounds, and we don't know how to deal with that kind of a problem yet. So all we can do is kind of use some properties that we know here, and maybe this information that they're giving us at the bottom to figure out this answer. So the first thing we can do is, since we have three different functions being added or subtracted, we can split this into three separate integrals. 1/2, x cubed, 3x, and 2. So how are we going to determine each of these three different integrals? If you take a look at what's given to you in the original problem, we know that the integral from 2 to 4 of x cubed dx is equal to 60. And since we see that same exact integral right here, we can just replace that with the number 60. How they got that, where they got that, doesn't really matter. All we know is that's equal to 60, so we can replace that with a 60. Same thing goes for the next integral. We know that the integral from 2 to 4 of x dx is equal to 6. So we can take those two and switch or substitute in form. So it's going to be 3 times 6. And then in the last piece of information that we're given, the integral from 2 to 4 dx is just equal to 2. But don't forget that there's still a 2 there in front of the integral, so it'll be 2 times 2. When you do that math, you'll end up with 16. So again, don't lose sight of this new concept that we learned. This is the area under this curve from 2 to 4. Okay, next example here, we're given two different integrals. We're given that the integral from 0 to 5 of some function that we don't know is 10. And we're also given that the integral from 5 to 7 of some function f that we don't know is equal to 3. And we're going to evaluate three different integrals here. What would be the integral from 0 to 7? Well, again, this represents the area from 0 to 7. We know that the area from 0 to 5 is 10, and we know that the area from 5 to 7 is 3. So this is trying to get us to see or to use that additive property for integrals. We know that the integral from 0 to 5 plus 5 to 7 would be equal to the total integral of 0 to 7. And since we know 0 to 5 is 10 and 5 to 7 is 3, we can simply add those up and get a total value of 13. In part B, we want to find the integral from 5 to 0 of f of x dx. Something hopefully is standing out right away for you because something isn't quite written right. The smaller number should be the lower bound. And again, that's not a big deal. If you refer to that last slide, we can switch those bounds. We just have to put a negative in front of the integral. And back from the original problem, we know that the integral from 0 to 5, or the area from 0 to 5, is 10. So we would have a final value of negative 10. In this last example, we have 3 times f of x, and we want to find the area from 0 to 5. We can take that 3 and factor it out to the front. Once we do that, we again already know that the integral, or the area, from 0 to 5 is 10. So we can simply just take this value and replace it with a 10. 3 times 10, of course, is just 30. Okay, one last example here. We have a graph that consists of line segments and a semicircle. We want to evaluate each definite integral using geometric formulas. And again, the reason we have to is we really haven't been equipped yet with dealing with these bounds on these problems. And even more so, we don't even know what the function is here. So we would definitely need some other way of doing this problem. So geometric is the way we're going to have to go. This integral is telling you to find the area from -4 to -2 of your function f, and this graph represents the function of f. So that's what we're going to do. That area is a triangle. From -4 to -2, we have a triangle. The thing you're going to have to keep in mind, though, is that since this triangle is below the x-axis, I guess shade it in here real quick so you can see exactly what I'm looking at. Since this triangle is below the x-axis, we're going to need to put a negative in front of our formula. which is of course 1/2 base times height. The base of this triangle is 2, the height of this triangle is 1, and when you multiply all that, you get -1. The next definite integral we want to evaluate is from -2 to 2. From -2 to 2, we're dealing with our semicircle. But just like with the triangle we just did, that semicircle is below the x-axis. So it's not just pi r squared divided by 2, it would be the negative version of that. In this case, the radius of this circle would be 2. When you simplify this fraction, you'll just end up with -2 pi. The next definite integral we want to evaluate is the definite integral from 2 to 6. In other words, we want to find the area under the function f from 2 to 6. Well, that shape is another triangle. Not a right triangle like we saw in the first one, but still a triangle. In this case, our triangle is above the x-axis, so it's still the formula 1/2 base times height, but it's positive since our area is above the x-axis. The base of this triangle is 4, the height of this triangle is 2, and when we multiply those numbers, we get 4. So not too bad. 3 fairly straightforward areas to find, but again, you have to tie together the fact that this definite integral in each of these problems is asking you to find the area. And in this case, since we're not dealing with some sort of wavy kind of function, and it's just simple geometry, we can find those areas quite simply. In the last part of this problem, we kind of need to step it up a little bit, and here we're being asked to find the integral from -4 to 6 of f of x plus 2 dx. Might seem a little bit confusing at first, but the very first thing we should realize in terms of how we should approach this problem is since we're adding two separate things, we can write two separate integrals. So that's the first thing we're going to do. We're going to write the integral from -4 to 6 of f of x, and then we're going to add to that the integral from -4 to 6 of just 2 dx. So let's talk about the integral from -4 to 6 of f of x. Well, that is just represented by all the areas we just found. If we want to find the area from -4 to 6 of f of x, I would have to take what I labeled as A1, which is the triangle, and add to that what I labeled as A2, which is the semicircle, and add to that what I labeled as A3, which is that last triangle. So we know to find the area from -4 to 6, I would just need to take all those areas and add them up. So how are we going to find the area from -4 to 6 of 2 dx? Well, we're going to have to graph 2 as a function. We don't know what the f function is. We just have this set of straight lines and a semicircle, so we don't know what the function f is, but it's graphed for us. Could we graph the function 2? Well, yes. This line that I just drew is the function y equals 2. And if we want to find the area of that, you'll notice if I draw these vertical lines here, and you can annotate this on your notes if you want, it's going to draw a shape if I connect all of that, I suppose, and close it in. That shape is, of course, a rectangle, and I'm going to call that area A4. So if I want to find the area of that rectangle, which is represented by the integral from -4 to 6 of 2 dx, I can just simply use the formula base times height. The base of this rectangle is 10, the height of this rectangle is 2, and that area is 20. So this area right here from -4 to 6 of 2 dx, which is just a rectangle, is 20. And now we can put all those values that we know, A1, A2, A3, and A4, put all of those values in and simplify the answer. So A1 was -1, A2 was -2 pi, A3 was 4, A4 was 20, and if we take 20 plus 4 and subtract 1, we'll get 23, and then -2 pi. So again, keep in mind this idea that a definite integral is telling you to find the area under a curve and above the x-axis, or I suppose below the x-axis, depending on how the graph is drawn.